Hey all, in today's lesson we're going to talk about some segments, those segments that we talked about way at the beginning of the circles unit, and how they interact with circles. So one way we can have segments interacting is if we have two tangent lines. Again, tangent lines just touch the circle at one point, so at A and C. And if I have two tangent lines that intersect at point B here, outside of the circle, then I know that the segments they create are going to be equal. So segment AB and segment BC have the same length. So we can say AB and BC are congruent. So the way you might see a problem like that presented is like this. We have a circle inside of a triangle, and we're given a few lengths. So these are all tangent segments. They all touch the circle at just one point. So we know that some things here are going to be equal. So this side, or this piece that's 10 centimeters, is going to be the same as this piece. This piece that's 15 centimeters is going to be the same as this piece. They're two tangents intersecting. And then this piece right here that's 8 will be the same as this one. So now that we know all the pieces to the puzzle, we can find perimeter, which is just adding all of these pieces up. So the perimeter is all of those pieces added together, which gives us a total of 66 centimeters. So go ahead, pause, and give this one a shot. Find the perimeter of this triangle. So just like in the last one, I'm going to go through and I'm going to label all the pieces I don't know. This one that's 17 is going to be the same as this one. The one that's 12 will be the same as this one here. And then these two are both 15. So, and again, perimeter, we just add up all the sides of the triangle. So all these pieces added together will give you 88 centimeters. So another way we have segments interacting is if we have two chords. So the chords are going to meet inside of the circle because that's where chords live. They live inside of the circle. And we're going to have a relationship. So this chord here gets split up into two pieces, two smaller segments. Same thing happens here with this chord. It's split into two smaller segments. And the relationship we have is that the two smaller segments from the first chord, if I multiply those lengths together, that's going to be equal to if I take the two smaller segments from the other chord and multiply their lengths together. So obviously the segments are not always going to be called A, B, C, and D, but it's one chord, the two little segments multiplied, it's equal to the other chord's two little segments multiplied. So let's see how that works. I have a chord here that's broken up into one segment that's 6.5 and one segment that's M. So we can multiply those two values together, and then we can multiply this little piece that's 3 times this little piece that's 7. And then all we have to do is solve this equation and find that this M is approximately 3.23. So go ahead and pause here and find the value of X. So again, two chords intersecting inside, we have four smaller segments that are created. So this chord makes a segment that's 10 and a segment that's X that we're looking for. So we'll multiply those two together. This chord has a segment that's 9 and one that's 6. We'll multiply those two together and we'll set them equal. Again, once we do that, we're just solving an equation and we get that X is 5.4. So this green segment is 5.4. The last relationship we have exists in two ways. We can either have a tangent line or a secant line intersecting outside the circle, or we can have two secant lines intersecting outside the circle. Both instances create the same relationship. So I'm going to talk first about this one on the right, and then we'll talk about how that applies to the one on the left. So when I have this situation with two secants, in each of these secants I have a little segment that's formed outside of the circle. So each of these secants have a small segment. Of course, inside I have another smaller segment. Those are called chords. And then I also have segments formed by the intersection and this intersection with the circle, and we're going to call those the whole segments. So all that mess, and I'll get rid of those, all that mess turns into this relationship. The outside of one secant segment times the whole thing is equal to the outside of the other secant segment times the whole thing. So sometimes I'll have students write this as, that's not going to work for me. Sometimes I'll have students write this as OW equals OW. And I'm struggling writing that, so OW equals OW, OW equals OW. Those are some ways to remember this. Or you can remember outside times whole equals outside times whole. So let's talk about this picture on the left, because it's a little different. This secant still has an outside piece, and it has the whole piece. My tangent line doesn't go through the circle, so there's only one segment to talk about right there. So we're going to take whatever that value is for this blue tangent segment, and we're going to say that that's the outside and it's the whole. So it goes in for both spots in the equation. So let's work a couple of these problems. So here I have two secants. So I'm going to first start with my formula, outside times whole equals outside times whole. And the outside of this top secant is 14. The whole thing is going to be the outside plus the inside. So the whole thing is 20 plus 14, which is 34. Similarly, I have the outside of this bottom secant, which is 16. That goes here. And the whole thing is 16 plus x. So that's how we get this 16 plus x. And we put it in parentheses because it represents one value. So now we'll distribute the 16. So 16 times 16 and then 16 times x. And we can just solve that equation to find that this inside piece is 13.75. So go ahead and try this one with a secant and tangent segment. So I'll start with the secant. The secant has an outside of 6, and the whole thing is 6 plus 15. So the whole thing is 21. And remember, for a tangent, we only have one piece, so that's the outside and the whole. So we'll plug x in for both of those. And I, of course, broke my rule. I didn't write the formula, so make sure you write outside times whole equals outside times whole. So there's my tangent segment, plugging x in for both, and then 6 from the outside times 21, which is the whole thing. To get x, to get rid of the squared, we square root both sides, and to get x to be approximately 11.2. So go ahead and try these two problems, and we will discuss them in class if you have questions.